Okay, so we're going from names here. So we have to brush up on our naming skills. And we also are going to be practicing predicting chemical reactions here, okay? So, sodium chromate. We should know, well, sodium is Na, and it is in the group 1, so it always has a charge of +1. Okay? And then chromate is a polyatomic ion. Okay, so I'm going to find it at the top of the, right up here. Chromate is CrO4 minus 2. Okay, so sodium chromate, if we have a -2 charge on the chromate and we have a +1 on the sodium, we need 2 sodiums, so it has a net charge of 0. So Na2 CrO4 reacts with, so remember this is like putting in a plus sign, okay, reacts with potassium nitrite. So potassium, again, it's a group 1 metal, so it always has a charge of +1. And nitrite is a polyatomic ion as well, and I see it on there, it's NO2 minus. So if potassium has a charge of +1, nitrite has a charge of -1, those will just have a net charge of 0. So KNO2. Okay, and the arrow reads 2 forms. So we know our cations are sodium and potassium. So those two are going to swap. Okay, so sodium is going to be going with nitrite, right? So we have Na, nitrite has a charge of -1, so NO2, okay? And what else is going to swap? My board is uncalibrated today. What else are we going to swap is the other cation, sorry about that. So potassium and chromate are going to swap. But potassium has a charge of +1 and chromate has a charge of -2. So I need 2 potassiums to balance that. Okay, 2, and then we're going to have our CrO4. Okay, now that we have predicted our products, we need to make sure this is balanced. So I'm just going to take a look at this. I see 2 sodiums and only 1 sodium there. So I'm just going to put a 2 up there. Now I have 2 sodiums, so sodiums are balanced. I have 2 nitrites going out, and I only have 1 nitrite going in. So I'll fix that. I have 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, and 2 sodiums. Okay, so that is our final answer. Give me a thumbs up if you got that one right. Yeah, perfect. Okay, so for those other students, make sure you are able to predict chemical reactions. Okay, that is going to be on the quiz on Thursday for sure. I believe there's 6 of them. Okay, so make sure you guys are able to do this. All right. Okay, so today we are going to be talking about thermal energy transfer between like a variety of substances. Yeah, right there. Yep. Phase changes is going to be your first one. Okay, this is just a title one. So phase changes is your first one, I believe. Okay. So we're going to be calculating the energy transfer when something either cools up or cools down. Okay. Here's the first one that you guys are going to recognize on there. Okay, if you're looking for it. So we're going to be calculating the thermal energy transfer either when something heats up and there is no phase change. Okay, so you guys have a couple formulas we're introducing today. So this is when there is no phase change, so Q is equal to MC delta T. And then when there is a phase change, so when something's going from a liquid to a gas, or when something's going from a solid to a liquid, we're going to use these two formulas over here, okay? So that's number one. So when there is a phase change, we're going to use these two. And when there's just a change in temperature, we will use this formula here, okay? Yeah, so water is a pretty unique molecule or compound, okay? It is able to hold a lot of energy when heated, right? And I'm sure none of you guys have done this, but this is true. Like if you were to stick your hand in like a boiling pot of water, right, that would be quite painful, not very fun, right? But if you were to stick your hand in an oven that was at 100 degrees Celsius, you wouldn't be burned, right? Like if you just put your arm in there to like maybe take out your pizza pops or whatever you guys cook, right? If you put your arms in there, you're not going to burn as you would if you stuck your hands into a boiling pot of water. This is because water is a better conductor of heat than air is, right? So yeah, we could walk in, if we were like, if there's a really big oven, you could go in there for like a short period of time and come out and be okay, right? But if you were to walk into like 100 Celsius pot of water, you would burn and you would probably die, right? So water is able to hold a lot of energy, okay? So with respect to areas on Earth, regions that have smaller amounts of water will tend to heat and cool faster than those regions that are at similar or that are near water. Okay, so for example, like Lethbridge and Vauxhall, we are in the middle of the prairies essentially, right? So we are susceptible to like really large swings in temperatures, right? Like what was it like 3 weeks ago? Not even. It was minus 30, minus 40, right? And then this weekend it's supposed to be 16 degrees above, right? So this is because we don't have a big body of water to regulate the temperature changes that we experience here. If we were to compare that to Vancouver, right, they are right on the ocean, right? So the ocean itself is going to regulate the temperature to some extent, so there's not such wide temperature swings there, right? Because the ocean stores a decent amount of energy. Okay, so these graphs are called climatographs. Okay, don't worry too much about them. But this is just showing the large temperature variations that we experience. This is in Lethbridge and this is in Vancouver. Okay, so like in this, well, the lowest is -15 and the positive is, or the highest is positive 25. So that's like a 40-degree temperature change, right? If we look at Vancouver, right, typically, you know, it gets around like 18, 19 degrees in the summer, but in the cold months, it's, you know, stays about like 2 or 3 degrees, right? So it only has like a 15-degree temperature change between winter and summer, and that's because they are so close to the ocean. Okay, the ocean is going to regulate the climate to some extent. Okay, so specific heat capacity, that is this one right here. Okay, so various substances are going to have different heating capacities. So water is going to have different heating capacity than like oil would, right? Cooking oil. So C is a specific heat capacity of substance, of any substance. Like I said, water is going to be different than oil, which is going to be different than like iced tea, right? So this value here is the amount of energy required to raise the temperature of 1 gram of the substance. I should change that, of the substance by 1 degree Celsius, okay? In this case, so this is the specific heat capacity of water. So this is the C value. C is specific heat capacity, okay? So the C value of water is 4.19 joules per gram degree Celsius, meaning to raise 1 gram of water in this case by 1 degree Celsius, we need to add 4.19 joules of energy. Okay, joules is just a unit of measurement for like thermal energy, okay? So that's what a joule is. And then we also have the specific heat capacity of aluminum, which is 0.97 joules per gram degree Celsius, okay? So this means, what does this mean? The specific heat capacity of water is larger than that of aluminum, meaning we need to put in more energy to raise 1 gram of that substance by 1 degree Celsius, okay? So to raise the temperature of 1 gram of water, you need 4.19 joules, and to increase the mass of 1 gram of aluminum, you're going to need 0.897 joules, okay? This is good, okay? So I have a question for you guys. Oh, maybe not yet. So metals are generally good conductors of thermal energy. Remember, the C of aluminum was lower than the C of water, right? So we have conductors and we have insulators. So insulators are going to want to like keep the heat in, right? Like insulation, we put insulation in our buildings to keep the heat in. And conductors, metals are conductors, and metals will allow electrons to flow usually, right? That's why we use like copper wiring for our lights, okay? So would the specific heat capacity, so remember that is the amount of energy required to raise 1 gram of the substance by 1 degree Celsius, right? So would the specific heat capacity of a metal or a conductor be higher or lower than the specific heat capacity of an insulator? So conductors, so metal, versus insulators. Which are like wood. What is going to have a higher C value? What are we going to have to put more energy in to increase the temperature of? Wood or metal? Wood, right? Yeah, perfect. So insulators will have a higher C value, right? Because we want to keep the heat in with insulators, right? So we want to have a high C value, so it needs more energy to increase the temperature, right? So we want to have a higher C value, whereas like metals, I should spell that right, metal, okay? Metals are going to have a low specific heat capacity because we don't want to invest a whole lot of energy into warming something up, right? Like we use, like frying pans are made out of metal, right? So we want to have a low specific heat capacity, so we don't need to invest a whole lot of energy to just warm up our frying pan, right? We want that energy to be transferred from the oven through the frying pan onto whatever it is that we're cooking, right? Okay. So that's our C value. So this is going to be different for each different substance, okay? Okay, I'm going to back up one now. So now here is your thermal energy calculations. Here is a formula. Again, this is when there is no phase change. No phase change here. Okay, the only, there's no phase change, but we do have a change in temperature. Okay, anytime you see this little triangle, This means the change in anything. Okay, so a little triangle, we call that a delta. Okay, so this is read delta T, and this is just saying how is the temperature changing. Okay, so if I'm going on a diet and I want to find my delta M, that would be my change in mass. Okay? So any time you see a delta equals change. Okay? Mass is not going to be changing. That was just my diet example. Okay? So in this case, mass is not going to be changing, but you guys just need to know that delta is change. Okay? That's the first time you guys would have seen that today. So delta means change. And we're going to deal with that a little bit more in the physics unit. Okay? Okay. Another thing we need to make note of here is that M is our mass of the substance, and that is in grams. Okay? That is different from our phase changes formula. Here we are dealing with moles. Okay? We're dealing with moles in this one. We both have N. And in this case, we're dealing with the grams of the sample. Okay? So not moles, grams. So just be careful about that. C, again, it's going to be unique to each substance. And delta T is a change in temperature. And the units of that are degrees Celsius. Okay? So the units for this will be grams. Any questions about this guy here? Oh. Perfect. So again, we use this formula when there's no phase change, only delta T, only when there is a change in temperature. Okay? Alright. Then you will be given this formula on the quiz and on the test. Okay, so we're getting into an example here. So the question is, how much thermal energy is required to raise the temperature of 3 grams of gold by 6.5 degrees Celsius? Okay, so here we only have a temperature change, right? Only have a temperature change, so we're going to be using this formula here, okay? So anytime that you're given a word problem like this, you're going to want to write down your variables, what we know. Okay, so what's given in the question. So we are asked, what is our Q? Okay, how much thermal energy is required to raise the temperature of 3 grams of gold. So mass is 3 grams. And we're changing the temperature by 6.5 degrees Celsius, okay, and we're increasing it. So the delta T, the change in temperature, is 6.5 degrees Celsius. Okay, and we also know the specific heat capacity of gold is 0.126 joules per gram degree Celsius. Okay, so we have M, T, and C. So now we can just put that into this formula and solve for Q. Okay, so Q is equal to MC delta T, so I'm just going to substitute those in. So we have 3 grams is my mass. My C is 0.126 joules per gram degree Celsius. And I'm multiplying that by my change in temperature, which is 6.5 degrees Celsius. Okay, so when you multiply this, your degrees Celsius will cancel, your grams will cancel, and you're just going to be left with joules, which is perfect. because that's how we measure Q, is in joules. So Q is equal to, I have 3 times 0.126 times 6.5. So I have Q is equal to 2.457 joules. And we have 2 digits, 3 digits, and 2 digits. So if you want to answer this with significant digits, you would report your answer to 2 digits. Okay, it's going to be whatever has the least amount of significant digits. But at this point, I'm okay if you guys leave your answer like this. Okay, when we get to the physics unit, you need to use sig digs. Okay, so this is fine, but if you want it to be have the best answer, you would have 2.5 joules, and put a box around it so I know what your answer is. Okay. All good with that one? Pretty straightforward, right? Mm-hmm. All right. Moving on. Okay, so now we're asked to calculate the change in temperature. So we're looking for delta T. That will occur if 1.25 kilojoules not kilograms, kilojoules of thermal energy is added to 150 grams of olive oil, and the specific heat capacity of olive oil is 2.10 joules per gram degree Celsius. Okay, so here are our variables. That's what we know. That's what the question's given. What are we solving for in this question? Delta T, right? So what is attached to delta T right now? Mass and C, the specific heat capacity, right? Because it's Q is equal to mass times C times delta T, right? And we're solving for delta T, so we need to get delta T all by itself, which it's not, right? So how are we going to get delta T by itself? We're multiplying delta T by mass and specific heat capacity, right? What's the opposite of multiplying? Dividing, okay? So we will divide both sides by mass and specific heat capacity. MC divided by MC equals 1. Okay, so we can just get rid of that. Now, do we have delta T all by itself? Yeah, right, so let's just rewrite that for delta T. So delta T is equal to Q over mass times the specific heat capacity. And now that T is all by itself, and we know Q, we know mass, we know our specific heat capacity, we can just punch that into our formula. Okay, so delta T. I want you guys to look at our Q, in particular the units on our Q and the units on C. What do we have here? This is kilojoules, and this is in joules. Yeah, so we need to fix this, okay? How do we fix that? Well, we know that 1,000 grams is equal to 1 kilogram, okay, which is kind of the same thing as saying 1,000 joules is equal to 1 kilojoule. Okay, so to get kilojoules to joules, we just need to multiply by 1,000. Okay, so 1.25 kilojoules is equal to 1,250 joules. 1, 2, 3, yeah. Okay, so now that we have our units, are proper, right? We have joules and grams and grams. Okay, we're all good. So now we can put that in. So delta T is equal to Q divided by MC. So Q is 1,250 joules divided by our mass, which is 150 grams, and multiplied by our C, which is 2.10 joules per gram degree Celsius. Okay, when we do this operation, our joules will cancel, our grams will cancel, and we're going to be left with degrees Celsius. And the change in temperature, we have 3 digits, 3 digits, 3 digits, so I will give this one to 3 digits. So delta T is equal to 3.97 degrees Celsius. Okay, so this question here, we're given the change in temperature, and we're just trying to find Q again. But I just want us to be careful with our change in temperature, okay? So anytime you're calculating the change in something, you're going to subtract the first temperature from the second temperature. Okay, so the change in temperature is equal to the first temperature subtracted from the second temperature, or you could also write this as temperature final minus temperature initial. Okay, so this is our final temperature, and this is our initial. Right, so final temperature is 22.5 degrees, right? And the initial temperature was 87 degrees Celsius. Okay, it's cooling, right? It's losing its temperature, so we should expect it to get a negative temperature change. 22.5 minus 87. So our change in temperature is negative 64.5 degrees Celsius. So now that we have our change in temperature, because we know our mass is 60 grams, and our specific heat capacity of glass is 0.840 joules per gram degree Celsius. We have our M, we have our C, and we have our delta T. So we can just punch that into our formula, and we can find the thermal energy released. So mass is 60. Oops. C is 0.840 joules per gram Celsius, multiplied by our change in temperature, which is negative 64.5 degrees Celsius. And our Q value, the thermal energy released, Q is equal to negative 3,250.8 joules. And kind of like how we changed our kilojoules to joules in the last question, we just multiplied by 1,000. If you want to go from joules to kilojoules, you'll just divide by 1,000. Okay, so let's divide by 1,000. Will give us negative 3.25 kilojoules. Okay, so the big takeaway from this problem is when you are finding the change in something, it is going to be your final minus the initial. Okay? All good? Okay. Okay, so now we are dealing with phase changes. So when you do have phase changes, you're going to use these two formulas here. Okay? Freezing, melting, evaporating, or condensing. This is called a phase change, right? We're changing our states of matter from like a solid to a liquid, or a liquid to a gas. Okay? So to melt a solid to a liquid, so if you have just like a hunk of ice, right, you need to add heat for that hunk of ice to melt, right? Or, going from that chunk of ice, if you melted it into water and then you continue heating it, eventually it's going to turn into steam, right? So when it goes from a solid to a liquid, we're going to use our heat of fusion formula. The formulas are the same. The only thing that changes between the two is that in the heat of fusion formulas, we're using the heat of fusion instead of the heat of vaporization. Okay, so they are different. So you just have to recognize if it's melting or if it's turning into a vapor. Like the specific heat capacity in our last formula, the heat of vaporization and the heat of fusion is going to be unique to that substance. Okay? It's going to be unique to that substance. Each substance will have its own heat of vaporization and heat of fusion. We will go over some of those. We'll go over that table soon. Okay, so when you are melting, you're going from a solid to a liquid, you're going to use heat of fusion. And when you're turning into a vapor, you're going to use heat of vaporization. Okay, so just make sure you know when to use each formula here. Don't worry too much about this heating curve of water, but this is just showing the temperatures at which the states of water do change, right? So from below 0 degrees Celsius, it's going to be solid, it's going to be ice, right? Between 0 and 100 degrees Celsius, it's going to be liquid water, right? And at 100 degrees Celsius and above, it's going to be a vapor. Okay, so this is just showing the heating curve of water. Okay. Any questions about this? Feeling all right? We already talked about this, so heat of vaporization. This is when you're going from a liquid to a gas. And heat of condensation, that's when you're going from the gas into a liquid. Don't worry too much about that one. Heat of vaporization and the heat of fusion, just these two formulas that we have up here, are what's going to be important for us. So, one thing you need to note, the heat of fusion and the heat of vaporization, so these two terms here, these are often given in kilojoules per mole. Kilojoules per mole. Okay, so just be careful with that. when we are doing our calculations, okay? That's fine though, because when we do this formula, usually our amount of heat is also going to be in kilojoules, which is going to work out well, okay? But just be careful with our units here, okay? So heat diffusion of water, well, I'll let you guys read the table. Okay, so it's just going to be different for each substance, okay? Another thing we need to make sure we know is that our N, we are in number of moles here, okay? We're not using masses, we're using number of moles. Okay, you guys on your sheet, I believe yours just says joules, right? Please cross that off and write kilojoules. Okay, because the heat of fusion, this is when we're melting something, or the heat of vaporization, they're both going to be given in kilojoules per mole. So some commonalities between our two formulas that we've talked about today. So Q is equal to MC delta T compared to Q is equal to N times heat of vaporization or heat of fusion. We both have Q, right? Anytime you see Q, you need to think of thermal energy. Okay? Think of thermal energy when you see Q. That is constant between the two. We have like a specific heat capacity or a heat of fusion or a heat of vaporization for that substance, so that is going to be unique to each substance. Okay, and we also we have like a mass in this formula here, and we're using moles, of course, in this one. Okay, so we have that N is moles from yesterday, right? Remember to calculate N. Does anybody remember that formula that we used yesterday? Yeah, perfect. N is equal to little m over big M. Very good. And so this is going from liquid to a gas, so we're going to be using our heat of vaporization. Okay, and it's pretty much the same formula, except we have heat of vaporization instead of heat of fusion. Okay, so the only thing that is changing between the two formulas is the heat of vaporization and the heat of fusion. Questions? All good? Okay. So, here we go. So, a liquid beaker containing 360.4 grams of water. Now, is that my N? Is that in moles? No, it's in grams, right? So we're going to need to fix that. So where do I want to do that? Let's go right here. So mass is 360.4 grams, and this is of H2O. So let's go ahead and calculate the amount of moles that we have first. Okay? So we have little m, which is the mass of our sample. Where do I write that? Okay. So we have our mass of sample. Now we need to find the molar mass. So water is H2O. Okay, you guys need to know that water is H2O. Okay, I don't think that should be too big of a stretch. So how many hydrogens are there in H2O? 2. Okay, so we're going to go 1.01 grams per mole. that is the molar mass of hydrogen, times 2, plus the molar mass of oxygen, which is 16 grams per mole. We're going to add those. So we will get molar mass of water is equal to 18.02 grams per mole. Okay, the molar mass of water will always be 18.02 grams per mole. Okay, will always be this mass, the molar mass. In like quizzes and tests and stuff, after you have shown me how to calculate the molar mass of water one time, okay, you don't need to do it for every calculation. Okay, so once you're like, okay, Mr. Jones, this is how I calculate the molar mass of water. If you have 2 questions that involve water and like the molar mass and stuff like that, you don't need to show this calculation again. You just need to show it to me once, okay? But if you want to just be safe, you can do that calculation too, okay? So molar mass is 18.02 grams per mole. So now we have N is equal to little m over big M. So the mass of our sample, how much water do we have? Perfect. Okay. This is the mass of our sample. So 360.4 grams divided by 18.02 grams per mole. When you divide this, your grams will cancel and you will be left with moles. So that gives me a value of 20 moles, which is equal to N. Okay, we are given our heat of vaporization of water, which is right here, and you will be given that also on a formula sheet. Okay, so now that we have our moles and we know our heat of vaporization of water, okay, we can just plug that into our formula and find our Q. So Q is equal to 20 moles multiplied by the heat of vaporization of water, which is 40.65 kilojoules per mole. So when I multiply those, moles over moles will cancel. I will be left with kilojoules. And I see 3 digits, 3 digits, 4 digits, 4 digits. So I'm going to give it in 3 digits, my answer. Which is perfect. I get 813 joules or kilojoules? Kilojoules. Good. How are we feeling? Good? Okay, you guys try this one on your own, please. Okay, so the first step that we need to do here is find how many moles we have, right? Because we are not using masses, right? The formula is Q is equal to number of moles multiplied by the heat of fusion. Okay, so number 1, we need to find moles. Okay, so the mass of our sample, that's like what's going to be in the question. Okay, that's going to be the mass of the sample. So in this case, we have 243 grams. And the molar mass of water, which we calculated last slide, is always going to be 18.02 grams per mole. Okay, when you do this, your grams cancel. And how many moles do we have? 13.5 moles. and that is our N value. Okay, now step 2, we need to find Q, or calculate Q, right? Because now we know our number of moles, we just need to multiply that by the heat of fusion of water. Okay, why are we using heat of fusion in this case? Because it's melting, right? Yeah, perfect. We're going from ice to liquid, so we use heat of fusion. Good. So Q is equal to our number of moles, so 13.5 mole, multiplied by the heat of fusion of water, 6.01 kilojoules per mole. Moles will cancel, and we're left with kilojoules, which is, anybody want to share their answer?
81.125.
Perfect. 81.1, right? And we have 3 digits, 3 digits, and 3 digits, so we will round it to 3 if you want to be perfect. Tanner, you're fine. Yeah, okay. So 81.3 units. Oh, 81.1, thank you. And units on that? Kilojoules. Okay. How are we feeling about this stuff? Good? Do you guys want some practice now?
Yeah.
Perfect.